శ్రీనివాస్ భరత్ చెప్పు. గూగుల్ మీట్ లో కింద ఆఫ్ చేస్తావా? నేను ఆఫ్ చేసుకోవాలా? ఆఫ్ చేసిన. ఎక్కడ పైన? అవును అవును. చేంజ్ లేఅవుట్. ఆటో స్పాట్ లైట్. ఇప్పుడు ఏమవుతుంది? నేను కనపడను. షేర్ చేసుకోవచ్చు. ఓకే ఓకే అట్లా రైట్. ఓకే రెడీనా? ఆడియో వీడియో క్లియరా? ఇప్పుడు బాగానే ఉందా ఆడియో? ఓకే రైట్. So good afternoon, my dear student friends. I welcome you back to our online GATE coaching classes. And today's session will be very important session. We'll be discussing about simple bending theory. It's a very important topic in structural engineering. Actually, before we go to this particular topic, let me answer some of the doubts raised by some students in previous day's session. So majority of the issues were about the PPT and downloading the PPT. I once again repeat to you that the PPTs are available on the websites of University, JNT University Anantapur, JNT University Kakinada, and Yogi Vemana University Kadapa. So please refer to www.jntua.ac.in. The two PPTs of the 3-day session are uploaded to this website. So please download it from the JNTU Anantapur website. So B Parthasarathi20@gmail.com has asked a question. What type of load is acting when a bus is traveling on a road? So what type of load is acting when a bus is traveling on a road? This is the question he has raised. While a bus is traveling on the road, actually the entire load of the bus and the passengers is transferred as point loads through tires to the road surface. So this wherever the tires are there, the load will be transferred to the road point as a point load. But please remember, this is a moving load. This is a moving load. It's not a static load. It is a dynamic load. It is moving load. So that is the difference. Explain pure bending, where it occurred. Actually, I have already explained about this. If you have a simply supported beam or a cantilever, say let us take a cantilever beam which is subjected to a couple. There is no uniformly distributed load or there is no concentrated load acting on the cantilever beam. So a cantilever beam subjected to a couple will be subjected to pure bending. It will be subjected to pure bending. So please remember that. Similarly, if you take, I have already explained you one simply supported beam problem. In one simply supported beam problem, if you have 2 point loads acting at L/3 from each support, so the middle middle third portion, what we call the middle third portion, there is no shear force, there will be only bending moment. So that is again a pure bending case. So these are the examples of pure bending. So Mr. Shashank 199727 at gmail.com. Sir, what is the difference between point of inflection and point of contraflexion? Mr. Shashank, I have already explained this. The point of contraflexion is the point where the bending moment changes its sign, maybe from sagging to hogging or from hogging to sagging. Such a point is called the point of contraflexion. Point of inflection and point of contraflexion both are same. The same name. It's a different name, that's all. So whether you call it as a point of contraflexion or it is a point of inflection, it is same. Dunnavamshikrishna@gmail.com. He is asking, right hand side upward shear force is positive, then you told run right hand side negative. So Vamshi Krishna, I am once again clarifying you that sign convention can be followed as per one's choice. Right upwards negative sign convention which I have proposed is internationally accepted sign convention. So right upwards positive also you can take. You can take whatever sign convention you want to follow for shear force or bending moment. Right upwards negative is the sign convention which is acceptable to majority of the countries in the world. So that's why I proposed right upwards negative. But there is nothing wrong if you follow right upwards positive also. But only thing is, don't mix up the sign conventions within the same problem. Given the same, if you take one problem, off chest. Off chest. So there is no point. There is no point. You can follow any sign convention, whatever you want, whether this sign convention or even in case of bending moment also, I proposed sagging bending moment as positive bending moment and hogging bending moment as negative bending moment. I also said certain textbooks they use sagging as negative and hogging as positive also. So there is nothing wrong. We can use any sign convention, but only my request is don't mix up the two sign conventions. Don't mix up the two sign conventions. Anjali Madula, sir, give some live examples of different types of loads on the beam. So I have already given examples for point loads, UDLs, couples. I have already given in my video. Please refer to my video. (1669) 1A0114 at mids.ac.in. One can find whether hogging or sagging. How to find out whether it is hogging or sagging? So I explained this. What is hogging? What is sagging? So if you take any section, on the left hand side of the section, if the direction of the moment is clockwise, or on the right hand side if it is anti-clockwise, that is called as a sagging bending moment. I told you to remember the electrical wire, the sagging of electrical wires. So the sagging of electrical wires is an example for sagging bending moment. On the other hand, a hogging bending moment is to the left of the section if the moment is anti-clockwise, and to the right of the section the moment is clockwise, then it is called as a hogging bending moment. It is a hogging moment. I hope it is clear. 1669 1A0114 mids.ac.in. I request you to upload more problems to solve by ourselves. Yes, I will give you number of problems and also their solutions and also the explanations. By the time we close this 12 days session, I will upload many more problems and also their solutions. You can look up to them and solve them by yourself. muralivenkat117@gmail.com. Sir, in Poisson's ratio, negative sign is there or not? So, Mr. Murali Venkat, while explaining Poisson's ratio, we defined Poisson's ratio as the ratio of lateral strain to longitudinal strain. So, for most of the materials, the Poisson's ratio is positive. For certain anisotropic materials, or for certain foams, Poisson's ratio may become negative. So foam, for foam, the Poisson's ratio may become negative. But for all other materials, the Poisson's ratio is positive. So the rest of the questions are all about availability of the PPTs. They are very much available on the website. So I request all the students to please download the PPTs from the website. So before starting the class of today, I'll just switch on my video. Please bear in for 1 minute. So let us continue our discussion on simple bending theory. Today's topic is simple bending theory. So whenever a cantilever beam or simply supported beam or overhanging beam or a continuous beam or a portal frame, whatever structure you take, it is subjected to certain loading. When it is subjected to certain loading, bending takes place. Bending of the beam or the structural element takes place. So we are going to understand the simple bending theory, how these structures can be analyzed when they are under simple bending. Actually, the bending theory is a very complicated phenomenon. If you want to analyze the bending, in addition to bending, at every cross section there may be shear force, there may be a torsion, there may be some temperature stress. So if you consider all these, the bending theory becomes complicated. So to simplify the bending, to simplify the pure bending theory, certain assumptions are made in the bending theory. So let us try to understand these assumptions, which are very important. The first assumption in the theory of bending is the material of the beam is isotropic and homogeneous and follows Hooke's law. So what does this assumption means? The material of the beam is isotropic. Isotropic means the same elastic properties in all the direction. A material which is having exactly same elastic properties in all the direction is called as an isotropic material. So homogeneous material means it is the entire distribution of the molecules is homogeneous. So such a material is called as homogeneous material. So we are assuming that the beam material is isotropic and homogeneous. So whether it is concrete beam or whether it is steel beam or whether it is wooden beam or it is some other aluminum beam or rolled steel joist, whatever it is, we are assuming that the material of the beam is isotropic and homogeneous and it obeys Hooke's law. What is Hooke's law? A Hooke's law says that within the elastic limit, the stress is proportional to strain, or the stress by strain is constant. So that is Young's modulus. The linear stress by linear strain is Young's modulus, that is constant. This is what the assumption we are making in simple theory of bending. So this is the first assumption. So because of this assumption, the material is becoming isotropic, so it has got similar properties in all the direction, and it is a single material, homogeneous properties. That is why we are able to tackle the analysis very easily. So this is the effect of this assumption. If you take the second assumption, the stress induced is proportional to the strain, and the stress at any point does not exceed the elastic limit. So what does this mean? This means that all the loads which we are applying are such that the maximum stress that is generated within the material does not exceed the stress at the elastic limit. The stress at the elastic limit. So what happens if we cross the elastic limit? If we cross the elastic limit, we will go to yield point, then we go to plastic point, plastic zone, plastic limit. So the analysis becomes difficult. So here we are assuming that we are within the elastic limit, that is stress is proportional to strain. So that makes our life very simple in analyzing the structure for a simple bending. The third assumption, which is very important, is transverse section of the beam that were plane before bending remain plane after bending also. So see what is happening. You have taken a beam which is straight beam. So we have applied certain loads or moment. So because of this, the beam is bending like this, sagging, or the beam may hog up like this. So anything is possible. A sagging is possible or a hogging is possible. So whenever a sagging or hogging, that means bending is taking place. The bending is taking place. If you consider any plane, if you consider any plane, the plane remains now the transverse section of the beam at every plane, they remain plane even after bending. Plane and normal. They remain plane and normal. So there is no warping. We are not assuming that the planes become warped. No, we are not assuming. The plane still remains a plane and it is normal. Plane sections which are plane and normal remain plane and normal after bending also. So actually sometimes it is not possible. Actually, if you look at the actual scenario, in the actual scenario, after bending, the sections may not still remain plane and normal. There will be a certain amount of warpity or certain amount of angle that develop. But whatever that is developed, we are ignoring that. And we are assuming that the section remain plane and normal. The sections remain plane and normal even after bending. So what is the effect of this assumption? The effect of this assumption is that if you consider the strain at any point from the center of neutral axis of the beam, I will explain you what is the neutral axis in my next slide. So for the time being you listen this, you already know probably what is the central axis, a neutral axis. So because of this assumption, that is the plane normal sections of the beam remain plane even after bending. So that assumption, because of this assumption, the strain is proportional to the distance from the neutral axis. The strain is proportional to the distance from the neutral axis, or otherwise the variation of the strain, the variation of the bending strain, the variation of the strain with respect to the depth of the beam is a linear variation. A linear variation. We are not considering any second degree variation or third degree variation. We are ignoring that. So we are considering that the variation of the strain across the depth is linear. This is because of this particular assumption. What is the assumption? The plane normal sections of the beam remain plane even after bending. Plane normal sections which are plane and normal before bending, they remain plane even after bending. That is our assumption. So because of this assumption, we are assuming that the strain is proportional to the distance from the neutral axis, or otherwise the variation of the strain is linear across the depth of the beam. So this point you have to understand very clearly. The beam is initially straight and having uniform cross section. So the beam is not curved or not having variations along the length. We are assuming initially the beam is straight and has uniform cross section. The last assumption is the modulus of elasticity is same for the fibers of the beam under tension or compression. So what is happening in the simple bending theory? Whenever you apply certain bending, certain moment or certain load on the beam is bending. Okay, the beam is bending. Certain fibers of the beam undergo compression and certain fibers of the beam undergo tension. When the beam is bending, certain fibers of the beam undergo tension and certain fibers undergo compression. That means certain fibers elongate and certain fibers compress. Okay, that is what happens when you bend any beam. You can see, you can take any one scale, try to bend it. You can see certain fibers elongate and certain fibers they get compressed. Here we are assuming that the value of modulus of elasticity or Young's modulus is same for the beam material in tension and compression also. So actually there may be different stress strain curve in tension and compression. For a given material, the Young's modulus may be different in tension and in compression. They may not be exactly same. The Young's modulus may not be exactly same. But we are assuming, for the sake of analysis, we are assuming that the Young's modulus in tension and compression is same for a given material. So the E value is same in tension or compression. This makes the bending theory much more easy. Otherwise, we have to analyze certain part of the beam with different Young's modulus and another part of the beam with another different modulus, becomes it's complicated. So for deriving the bending theory, it is assumed that the modulus of elasticity for the material is same in both tension as well as the compression. So this is what we are assuming. The beam is now subjected to pure bending. So we are not considering any shear, we are not considering any torsion, we are considering that it is subjected to a pure bending. So when a beam is subjected to pure bending, it bends into a arc of a circle. Please note, whenever a beam is subjected to pure bending, it bends into an arc of circle. It bends into a circular arc. It bends into a circular arc. The radius of curvature is large compared to the dimensions of the section. This is another important assumption. The radius of curvature into which the beam bends is very large compared to the dimensions of the section. There is no resultant pull or push on the cross section of the beam. The next assumption. There is no resultant pull or push on the cross section of the beam. So the beam cross sections are not subjected to any pull or push. So it is subjected to pure bending. The loads are applied in the plane of bending. Yes, the loads are applied in the plane of bending only. So if you apply load in plane normal to the bending, then it will cause twisting. So we are not considering that. We are considering that the loads are applied in the plane of bending. The transverse section of the beam is symmetrical about a line passing through center of gravity in the plane of bending. So that transverse section, or what we call as the neutral axis, we will discuss now. So this is the simple bending equation. You all know this. M by I is equal to F by Y is equal to E by R. Or instead of F, we are using sigma. M by I is equal to sigma by Y is equal to E by R. M is moment of resistance. I is moment of inertia of the section about the neutral axis. E is the modulus of elasticity of the material. R is the radius of curvature. I said when the beam is subjected to bending, the beam bends into a circular arc. So that radius R is called as, the radius of the circular arc is called as radius of curvature of the neutral axis. Radius of curvature of neutral axis. sigma is the bending stress at any point, and y is the distance of a point from the neutral axis. So this is the simple bending equation. M by I is equal to sigma by y is equal to E by R. M is the bending moment or moment of resistance. I is the moment of inertia. Sigma is the bending stress. Y is the distance of the fiber from the neutral axis. E is the Young's modulus. R is the radius of curvature of the circular arc. So naturally from this sigma is equal to M by I into Y. So stress is directly proportional to its distance from the neutral axis. Stress is directly proportional to distance from the neutral axis. Bending stress is directly proportional to its distance from the neutral axis, or otherwise the variation of the bending stress across the cross section is linear. You see here, this is the variation of the bending stress. So this is the neutral axis. This is the neutral axis which passes through the centroid of the cross section. The neutral axis passes through the centroid of the cross section. So what is this neutral axis? I will explain you first. So let us first consider this particular simply supported beam. Here there is a cantilever beam. This is a simply supported beam. So let us consider first this simply supported beam. Now if this simply supported beam is subjected to bending, this will sag like this. Okay, this will sag like this. So because of this sagging, what is happening? Fibers in the bottom side are getting elongated and fibers in the top side are getting compressed. So the bottom fibers are subjected to elongation and the top fibers are subjected to compression. So when you go from bottom to top, naturally we reach a point where there is neither compression nor elongation. There is neither reduction in length nor elongation. So such a point or such an axis where there is neither compression or tension is called neutral axis. The neutral axis always passes through the centroid of the cross section. The neutral axis always passes through the centroid of the cross section. So what is neutral axis after all? Neutral axis is the axis on which there is no strain. That is, neither there is no reduction in the length nor there is no increase in the length. So such an axis is called a neutral axis. So the strain on the neutral axis is equal to 0. So once the strain is equal to 0, what will happen to the stress? Stress is equal to strain into Young's modulus. So naturally the stress is also equal to 0. So at neutral axis, both stress and strain are equal to 0. So that axis is called as a neutral axis. So if you see here, if you see this cantilever beam, just like a cantilever beam, now it is subjected to downward loading. If it is subjected to downward loading, cantilever beam hogging takes place. It hogs up like this. So when it hogs up like this, what happens now? Fibers at the top zone will try to elongate and fibers at the bottom try to compress or reduce in the length. Just opposite to simply supported beam. Simply supported beam is sagging due to vertical loading, downward loading, whereas cantilever beam hogs up due to downward loading. So because of this hogging in cantilever beam, tensile strains will be there in the upper part and compressive strains will be there in the lower part. So as we go from bottom to top, again there is one layer, again there is one fiber where there is neither compression nor tension. Such axis is called as the neutral axis. So whether you take a simply supported beam or you take a cantilever or whatever it is, neutral axis is the axis of the fiber where there is neither strain nor stress, or otherwise stress is equal to 0, strain is also equal to 0. That such an axis is called as neutral axis. And please remember, neutral axis always passes through the centroid of the cross section. It always passes through the centroid of the cross section. So here if you see, if we take this cantilever beam, we call all the zone above the neutral axis as the tension zone. All the zone above the neutral axis is the tension zone. All the zone below the neutral axis is called as a compression zone. So because below the neutral axis there is compression here, and above the neutral axis there is tension. So compressive stresses will be there below the neutral axis, and tensile stresses will be there in the above the neutral axis in case of a cantilever beam subjected to downward loading. So if you take a simply supported beam subjected to downward loading, it sacks up. So because of sagging below the neutral axis, we call it as the tensile zone, and above the neutral axis we call it as the compression zone. Below the neutral axis we call tensile zone, and above the neutral axis we call compression zone. So whenever you design a simply supported beam, tensile stresses will be developed below the neutral axis, and compressive stresses will be there in the above the neutral axis. So if you are designing a RCC beam, if you are designing a RCC, reinforced concrete beam, concrete is very strong in tension, compression, and very weak in tension. So that is why we make RCC by providing steel reinforcement. So where the steel reinforcement is to be provided, wherever there is tensile stress, we have to provide the steel reinforcement. So if you take a simply supported beam, tensile stresses are at the bottom side. So that is why in simply supported beams we provide steel reinforcement at the bottom. In the compression zone, there is no tension in the compression zone. Concrete is capable of taking the compression. So we don't provide any steel reinforcement above the neutral axis in case of a simply supported beam. On the other hand, if you take a cantilever, say for example, if you take a balcony or a cheggia, a portico, where it's a cantilevered structure, you can see tensile stresses are developing above the neutral axis. So the tension zone is at the top. So the steel reinforcement in RCC porticos or cheggias is placed at the top, not at the bottom. So you have to be careful. So tensile stresses come in the top zone. So that is why we provide steel reinforcement in the top in case of a cantilevered portico or cheggia or balcony, etc. So this is the concept. Whenever a beam bends, certain fibers elongate and certain fibers they get compressed. So in between there is one fiber which neither undergoes compression nor tension. Such a fiber is called as a neutral axis. Such a fiber is called as a neutral axis. So the strain on the neutral axis is equal to 0. Because the strain is equal to 0, the stress is always 0 at the neutral axis. So here if you see the variation of the bending stress, if you see here, this is the neutral axis. So in case of a simply supported beam, above the neutral axis we have compression zone, so compressive stresses, and below the neutral axis we have tensile stresses. So like that, in case of a cantilever beam, it will reverse. So if you are putting sagging positive and tensile stresses positive, compressive stresses negative, or whether you are putting compressive stresses positive or tensile stresses negative. So whatever sign convention you follow, you have to adopt accordingly. So if you follow that tensile stress is positive and compressive stress is negative, so this indicates a cantilever, a stress distribution in a cantilever. If you say compressive stress is negative and tensile stress is positive, this indicates a simply supported beam. So depending upon the sign convention, so there is you have to follow a pakka sign convention. That's it. The stress, what you have to remember here is the stress distribution is a straight line. So it changes the sign from the neutral axis. It changes the sign from the neutral axis. So this is the variation of the bending stress. Just the same is the variation of the bending strain also. The strain also varies linearly. Across the depth of the beam. This is the depth of the beam. Across the depth of the beam, the strain also varies linearly. the strain also varies linearly. So in the working stress method of structural design, we follow this, both the stress and strain. In the working stress, the stresses are within the safety limit, within the safety factor. So we take the yield stress divided by factor of safety is the working stress or permissible stress. So that is the limit. So in such a case, it is well within the elastic limit, well within the elastic limit. That is why the stress is proportional to strain, and we assume that because the strain is linear, the bending stress is also linear. But please remember, when you go for limit state method of design, you go to limit state method of design, this differs. The strain variation is linear, but stress variation will not be linear. It will be a parabolic. We assume a parabolic variation. Okay. So if you are going to limit state design, this is not the variation of the bending stress. This is applicable only for the working stress method of design. So the variation of bending stress is linear here. But whether it is limit state method or working stress method, we assume the strain varies linearly. The strain varies, the distribution of the strain is linear. So if you take certain important definitions, we will go for defining what is called as section modulus. Section modulus, with reference to simple bending theory, we define what is called as section modulus. Section modulus is a property of the section. It is a property of the section. So we know that sigma, the bending stress, is equal to m by I into y. We know this from the bending theory. M by I is equal to sigma by y. We get sigma is equal to m by I into y, or it is m by z. If we write I by y as z, this can be written as m by z. So what is this z? Z is equal to I by y, and it is called as the section modulus. It is called as section modulus. What is y here? Y is the distance of the fiber, distance of the extreme fiber from the neutral axis. Distance of the extreme fiber from the neutral axis. So section modulus is the ratio of I by y, or moment of inertia divided by extreme fiber distance from the neutral axis. So section modulus is a very important definition in simple bending theory. So it is z is equal to I by y, moment of inertia divided by the extreme fiber distance. So if you see now, sigma is equal to m by z. So m is equal to sigma into z. So the maximum bending stress occurs at the extreme distance from the neutral axis. We know because sigma is equal to m by I into y. So sigma becomes maximum when y becomes maximum. So at the extreme fiber, the top fiber, we get the maximum stress. The maximum bending stress occurs at the top fiber of the neutral axis, from the neutral axis. So which is equal to sigma into z. Sigma into z. So for a given material of the beam, m is directly proportional to section modulus. Moment of resistance, or the moment carrying capacity of the beam, is directly proportional to z for a given material. For a given material of the beam, say if you are choosing an RCC beam or you are choosing a steel beam, for a given material of the beam, the moment of resistance or the carrying capacity of the beam is directly proportional to section modulus, directly proportional to the section modulus. So for a given material, a beam having higher section modulus will carry higher bending moment. That means higher loads. Okay. So the moment carrying capacity increases as the section modulus increases. So it is directly proportional to the section modulus. So let us consider a rectangular section, because this we will discuss some popular sections. We will consider a rectangular section. Okay. a rectangular section of width B, a rectangular section of width B and depth D. So where is the centroid for this? It is d by 2 from the top and d by 2 from the bottom. This is a centroid. So neutral axis passes through the centroid. So this distance is d by 2 and the bottom distance is d by 2 from the neutral axis. So this is the neutral axis. The distance is d by 2. This distance is d by 2. So the neutral axis is exactly at d by 2 from either top or the bottom. So for a rectangular section, what is moment of inertia? You know, the moment of inertia is equal to BD cubed by 12. So moment of inertia I is equal to BD cubed by 12. Now what is Y max for this section, rectangular section? Which is the top fiber? Top fiber is either at the top or the bottom. The extreme fibers are either at the top or at the bottom. So Y max is equal to D by 2. Y max is equal to D by 2. So the section modulus for a rectangular section is I by Y. I is BD cubed by 12 and Y is D by 2. So 1/6 BD square is the section modulus for a rectangular section. So for rectangular section, the section modulus is 1/6 of BD square and Y max is equal to D by 2. Y max is equal to D by 2. Now if you take a hollow rectangular section, a rectangular section is a total solid rectangle. Now we come to a hollow rectangular section where we'll see the outer width is B and the outer depth is D and the small hollow portion width is B and hollow portion depth is D. So this in between portion is the solid. In between this part is a solid part. So this is all no material. So material is there only in this portion. So the rest of the portion is hollow. This is hollow. So this is capital B, this is capital D. So if it is capital B, capital D, what is thickness of this rectangular section if you want? It is capital D minus small d. Okay, capital D minus small d by 2 will give you this thickness. Capital D minus small d by 2 will give you this thickness. Okay, so our small b minus small b, capital B minus small b by 2. That gives you the thickness in each direction. So for a hollow rectangular section with the capital B, capital D outer dimensions, small b and small d inner dimensions, the moment of inertia of the section about neutral axis is I is equal to 1/12 of capital BD cubed minus small bd cubed. So this is a rectangle, you know, BD cubed by 12. So we have two rectangles, one big rectangle BD cubed by 12. The small rectangle there is no material. So this is to be, we have to do minus. So minus small BD cubed by 12. So that is 1/12 of capital BD cubed minus small BD cubed. That is moment of inertia of the rectangular section, hollow rectangular section about its neutral axis. Again, the neutral axis is at a depth of capital D by 2 from the top or capital D by 2 from the bottom. The neutral axis always passes through the centroid. So Y max is again capital D by 2 now. Y max is capital D by 2. You can see here it is capital D by 2. This is total depth is D. So the extreme fiber distance is D by 2 from the neutral axis. So the section modulus is I by Y max. So BD cubed minus small bd cubed by 12 divided by capital D by 2. We get the section modulus Z is equal to capital BD cubed minus small bd cubed by 6D by 6 capital D. This is the section modulus for a hollow rectangular section. If you take a circular section, of diameter D, a circular section of the diameter D, for this also the neutral axis passes through the centroid, the center portion. Okay, so for circular section, the moment of inertia about the neutral axis is pi d to the power of 4 by 64, where d is the diameter. Pi d to the power of 4 by 64, where d is the diameter of the circular section. So what is the extreme fiber distance now? The extreme fiber distance is Y max is equal to half of the diameter, or it is equal to radius. Okay, so Y max is equal to D by 2. D by 2 is nothing but the radius of the circular section. So Z is section modulus is again I by Y max. I is pi to the power of 4 by 64 and Y max is D by 2. So pi to the power of 4 by 64 divided by D by 2 equal to half of the diameter. So if you substitute R, D is equal to 2R. If you substitute D is equal to 2R, we get Z is equal to pi R cubed by 4. So in terms of the diameter, Z is equal to pi D cubed by 32. And in terms of the radius, Z is equal to pi R cubed by 4. So this is for a solid circular section. So now if you go for a hollow circular section whose outer diameter is capital D and inner diameter is small d. Okay, inner diameter is small d. Just like rectangular section, this is all hollow portion. This is all the hollow portion in the inside. This is the solid portion. So in the solid portion only the material will be there. So moment of inertia is pi capital D to the power of 4 by 64 minus pi small d to the power of 4 by 64, or otherwise it is pi by 64 into capital D to the power of 4 minus small d to the power of 4. So that is the moment of inertia I. And in this case, what is the extreme fiber distance from the neutral axis now? It is naturally capital D by 2. The extreme fiber means the farthest fiber from the neutral axis. The fiber which is away, totally away from the neutral axis. So what is that? That is nothing but the D by 2 at a distance of D by 2 from the neutral axis. So farthest fiber is at a distance of D by 2 from the neutral axis, whether at the top or at the bottom. So Y max is equal to D by 2. So again, what is the section modulus? You simply substitute Z is equal to I by Y max. You get Z value as pi into capital D to the power of 4 minus small d to the power of 4 by 32 capital D is the section modulus for a hollow circular section. So sometimes we have observed that certain questions can be asked on flitched beams. A flitched beam is a beam reinforced symmetrically about the neutral axis by a different material. A flitched beam is a beam reinforced symmetrically about the neutral axis by a different material. Say for example, if you take a RCC beam, the RCC beam can be reinforced with steel plates. The RCC beam can be reinforced with steel plates. So like that. So two different materials are used here. Such a beam is called a flitched beam. Such a beam is called as a flitched beam. The reinforcement should be symmetrical about neutral axis. So if you use a reinforcement at the top of the neutral axis, above the neutral axis, you should also use it below the neutral axis. So symmetrical. It must be symmetrically reinforced. Flitched beams are used to withstand loads greater than normally allowable. So you have already you have designed certain section and found that higher loads are coming now. So you want to reinforce the existing section, you use flitched beams. We use flitched beams. Generally, the reinforcing material should have higher modulus of elasticity than the original material of the beam. So Young's modulus should be higher for the reinforcing material. So such a beam is called as a flitched beam. So when you take a flitched beam, the total resisting moment at any section is the sum of resisting moments caused by the individual materials making up of the section. There are two materials. So here the total moment of resistance M is equal to M1 plus M2. M1 is the resisting material of the beam material. M2 is the resisting moment of the reinforcing material. So original beam material is resisting M1 and the reinforcing material is resisting M2. So the total resistance of moment is M1 plus M2. So this is the equation in flitched beams. And each material will bend independently about its own neutral axis. Each material will bend independently about its own neutral axis, but to the same radius of curvature. In case of flitched beams, please note that In case of flitched beams, please note that each material will bend independently about its own neutral axis, but this radius of curvature remains the same for both materials. So if you take material 1, m1 by I1 is equal to sigma 1 by y1 is equal to E1 by R1. Similarly for material 2, m2 by I2 is equal to sigma 2 by y2 is equal to E2 by R2. So what is the radius of curvature here? Radius of curvature is equal to m1 by E1 I1 and m2 by E2 I2. So because the radius of curvature is same, we can write m1 by E1 I1 is equal to m2 by E2 I2. Similarly, we can write sigma 1 by y1 E1 is equal to sigma 2 by y2 E2. So the radius of curvature remains the same. The radius of curvature remains the same. So that is why m1 by E1 I1 is equal to m2 by E2 I2, or sigma 1 by E1 y1 is equal to sigma 2 by E2 by 2. This is valid for flitched beams. For flitched beams, you have to consider this concept. The concept is each material will bend independently about its own neutral axis to the same radius of curvature. So the radius of curvature is same for both materials. However, they bend independently about their own neutral axes. So according to that, we get m1 by E1 I1 is equal to m2 by E2 I2. Also sigma 1 by E1 y1 is equal to sigma 2 by E2 y2. So these two equations come from this particular concept for flitched beams. So here one example I am showing you. So this is the original material and this is the reinforcing material. Okay, the original material is having a width B and the reinforcing material is having a thickness of T on each side. So both sides we have placed. See, the reinforcing material is placed both sides. Both sides. If the two materials are joined firmly, so here this is the original beam material and this is the reinforcing material. If these two materials are joined firmly, then from the compatibility criteria, strain in material 1 must be equal to strain in material 2. So E1 is equal to E2. The strain in material 1 is equal to strain in material 2. E1 is equal to E2, or otherwise strain is stress by Young's modulus. Sigma 1 by E1 is equal to sigma 2 by E2. From this we get sigma 2 is equal to E2 by E1 into sigma 1. Sigma 2 is equal to E2 by E1 into sigma 1, or this E2 by E1 ratio is called as modular ratio. It is called as modular ratio. E1 is the Young's modulus of the original material. E2 is the Young's modulus of the reinforcing material. So the ratio E2 by E1 is called the modular ratio. Generally, E2 should be more than E1. E2 should be more than E1. So then only it is beneficial to reinforce. So modular ratio is generally greater than 1. So E2 by E1 is called as modular ratio M. So sigma 2 is M times sigma 1. This is the concept with flitched beams. So from this actually you can find out the moment of resistance. Moment of resistance is M is equal to sigma into section modulus. So M is equal to sigma into BD square by 6. So B becomes B plus 2MT into D square by 6. B becomes B plus 2M into T, because thickness is T here, 2T. 2T modular ratio times 2MT by 6 into D square. This is what we call as the equivalent section. Converting that into an equivalent section. So now we will come to beams of uniform strength. Beams of uniform strength. What does this mean? What is meant by a beam of uniform strength? Beam of uniform strengths are normally used to carry loads and bending moments that vary from section to section along the length. Generally, what is meant by a beam of uniform strength? The beam of uniform strength means at any section along the length of the beam if you take, at any section along the length of the beam if you take, the strength is same. What is meant by strength here? In the bending, the moment carrying capacity or the moment of resistance M is same along the length. Along the length. At any point, M is same. That such a beam is called as the beam of uniform strength. A beam of uniform strength is such a beam which has got same carrying capacity at any cross section. At any cross section along the length. In the beams of uniform section, the extreme fibers at all sections along the length are not stressed to maximum permissible bending stress, and hence this is a wastage of material takes place. The wastage of material takes place. So here if you see the governing equation here, we know sigma max is equal to m by z. So m is proportional to Z. We already seen M is equal to sigma into Z. So M is proportional to Z, the section modulus. So if at every section of the extreme fiber stress is equal to sigma max, then the section modulus of the beam at any section should be proportional to the bending moment at that section. So M is proportional to Z. So if we consider rectangular beams of uniform strength, we may keep the width constant and vary the depth, or we may keep the depth constant and vary the width along the length. So, or both width and depth can also be changed. So the most common way of keeping the beam of uniform strength is by keeping the width uniform and varying the depth. Generally, we vary the depth. We generally keep width uniform and vary the depth. The most popular examples are box girders, plate girders, latticed girders, or carriage springs, or even electrical poles, etc., where the depth is varied, the width is kept uniform, and the depth is varied to obtain a beam of uniform strength. For circular beams of uniform strength, the section can be made by varying diameter in such a way that M by Z is constant. You know, M is proportional to Z, so M by Z must be a constant. So like that you can design a circular beam. Now let us take different types of examples for this type of uniform beams. Beams of uniform strength. This is a very interesting topic. Beams of uniform strength is a very interesting topic for the examiners also. Lot of questions do come from this particular topic, beams of uniform strength. So that's why I am focusing slightly more on this topic, beams of uniform strength. So let us consider the cantilever carrying a concentrated load at the free end. Cantilever carrying a concentrated load at the free end. So take this. A cantilever of length L is carrying a concentrated load W at the free end. So if you consider any section X here, what is the bending moment here? Bending moment at any section is algebraic sum of all the moments either to the right or to the left of the section about the section. So there is only one load if you consider the right side. The moment is W into X. Okay, the moment is Wx. It is clockwise moment on the right side. So it is a hogging moment. So it is a negative moment as per our sign convention. It is a hogging bending moment. W into X. The Mx is equal to Wx. See here, Mx is equal to Wx. We know this is a rectangular section. So for a rectangular section, Z is equal to 1/6 BD square. 1/6 BD square. So what is bending stress now? Sigma is equal to M by Z. Sigma is equal to M by Z. So substitute M is equal to Wx. We get sigma is equal to 6Wx by BD square. 6Wx by BD square. So let us see two. Well, first we will keep depth constant and vary the width. Okay, let us keep the depth constant and vary the width. This criteria. So depth is constant, same depth, and we are varying the width. This is how it appears in the cross section. So in the previous slide we derived sigma is equal to 6Wx by BD square. So from this, what is B? B is equal to 6Wx by sigma d square. 6Wx by sigma d square. So that is the equation for Bx. Bx is the breadth at any section x. Okay, breadth at any section x at a distance of x from B at the free end. So if you consider this is Bx, Bx is equal to 6Wx by sigma d square. So accordingly, Bx is proportional to x. Bx is proportional to x. So from this, at x is equal to 0, if you see this section, at x is equal to 0, you put x is equal to 0, Bx is equal to 0. So there is no breadth is required at the free end. B is equal to 0. And at x is equal to L, if you substitute x is equal to L, it is 6WL by sigma d square. 6WL by sigma d square. So at x is equal to L, that means at A, at point A, we need a breadth of 6WL by sigma d square. D is constant. We have maintained D as a constant. Similarly, if we keep B is constant, if we keep the breadth constant and vary the depth. Now, see second case, we are varying the depth. Width is kept constant. So please see the way if you keep the depth constant and vary the breadth is proportional to x. So it is varying as a straight line. It is a straight line variation. It is a straight line variation. Let us see what happens when we keep B constant and vary the depth. If we keep the breadth constant and vary the depth from this particular equation, sigma is equal to 6Wx by BD square. What is D now? D square is equal to 6Wx by B sigma. 6Wx by B sigma, or D is equal to under root of 6Wx by B sigma. 6Wx by B sigma. So see here, the depth at any section dx is equal to 6Wx by B sigma under root. So this is the depth. So depth is proportional to square root of x. See here. So it is x to the power of half. So that's why you see a curve. It's not a straight line. It is a curve. So d is proportional to square root of x. It is proportional to square root of x. So from this you can see again, at x is equal to 0, that is at point B, at x is equal to 0 at point B, you know depth is becoming 0. So there is no depth is required. And at x is equal to L, so at this point at the fixed end, D is equal to root of 6WL by B sigma. B sigma. So the depth varies from 0 to 6WL by B sigma under root up to this point as a curved variation. So please remember, breadth is varying linearly, but depth is varying as square root of x. So that point you have to keep in mind. So this way, for any beam, if you want to design a uniform beam of uniform strength, if you want to design a beam of uniform strength, you have to follow these two criteria, whether you can design it keeping width constant and varying the depth, or keeping the depth constant and varying the width. But generally, most occasions we design keeping the width constant and varying the depth. But from theoretical point of view, the depth at the free end is 0. But practically it is never possible. We cannot keep a 0 depth, or without any depth we cannot keep the mid. So generally some minimum depth is provided even at the free end in practical designs. Here we are just understanding the theory, but in practice 0 depth will not be there. So minimum depth of the beam will be provided. So the guidelines for providing the minimum depths are available in IS codes. So accordingly we will provide the minimum depths. So let us consider a cantilever beam carrying a UDL, and we want to design beam of uniform strength. So again the same procedure. So if you consider a section at a distance of x here, the bending moment is equal to Wx into x by 2. The bending moment here is W into x is the load, into x by 2 is the moment. So Wx into x by 2, Wx square by 2 hogging. So that is the bending moment. You know, for rectangular section it is Section modulus is 1/6 of BD square. So again, what is stress sigma? Sigma is equal to M by Z. So sigma is equal to 3Wx square by BD square. So M is equal to Wx square by 2, that divided by Z is BD square by 6. So if you substitute that, you get sigma is equal to 3Wx square by BD square. So from this now, you have two options. Keep the depth constant and vary the width, or keep width constant and vary the depth. So two cases I have presented here. Two cases I have presented here. So same procedure, whatever we have discussed, same procedure. You find out Bx. Bx here, you see it is varying as second degree curve. So it is a parabolic variation. It is a UDL, that's why we are getting a parabolic variation. Similarly, keeping the breadth constant and varying the depth is now proportional to x, so that's why it is a straight line. That's why it is a straight line. So a cantilever subjected to a uniformly distributed load, if you want to design a beam of uniform strength, if you keep the width same and vary the depth, the variation of depth is linear. So it is self-explanatory. I have already explained for the previous case. The same way we can find out breadth and depth at x is equal to 0 and x is equal to L for this problem also. So now if we come to simply supported beam subjected to a point load at midspan, simply supported beam subjected to a point load W at the midspan. So each reaction will be W by 2, W by 2. So let us consider a section at a distance of x from the left end. So the reaction here is W by 2. So bending moment here is W by 2 into x sagging. Okay, W by 2 into x sagging. So if you see W by mx is W by 2 into x. Mx is equal to W by 2 into x. Z is equal to BD square by 6. So from this, sigma is equal to M by Z is equal to 3Wx by BD square. So from this, B is equal to 3Wx by sigma D square, or D is equal to square root of 3Wx by B sigma. Okay, square root of 3Wx by B sigma. So from this, sigma is equal to M by Z, we can get the equation for B or D. So again, two cases are possible. Keep the depth constant and vary the width, or keep width constant and vary the depth. Accordingly, we can get what is the width required. See here if you see, the maximum width is required here and zero width is required at the supports. Zero width is required at the support. Similarly, when you keep breadth constant and vary the depth, maximum depth is required at the midspan and zero depth is required at the supports. And see here, depth is proportional to root x, whereas width is proportional to x linearly. So this is a curved variation and this is a linear variation. So these concepts you have to keep in mind. Similarly, a simply supported beam with a UDL. Okay, so each reactions will be WL by 2, WL by 2. Each reaction is WL by 2, WL by 2. So the bending moment at a section X is WL by 2 into X sagging, WL by 2 into X sagging, minus WX square by 2, that is sagging. That's why minus WX square by 2. So WL by 2 is the reaction multiplied by X. It is sagging. WL by 2 into X. This UDL, this small UDL is there. So W of intensity W. So W into X is the load, into X by 2 is the moment at the section. So WX square by 2. So this is the bending moment. Z is BD square by 6. So sigma is equal to M by Z. Again, 3W by BD square into Lx minus X square. Lx minus X square. So keeping the width constant, keeping the depth constant, if you vary the width, this is the distribution, and keeping the width constant and varying the depth, this is the equation. So from this stress equation, again you can find out the distributions which are exactly the same way what I have explained for the cantilever. So this is how we can design beams of uniform cross sections. So now let us proceed to answer some questions which have appeared in the previous GATE examinations, keeping the concepts in the mind. Only important concept that you have to remember is M by I is equal to sigma by Y is equal to E by R. That is the only concept you have to remember. Rest of the things are very simple. They can be derived from this basic fundamental equation M by I is equal to sigma by Y is equal to E by R. So most of the questions will test your concept on this basic bending equation. If you know this basic bending equation, you can answer the GATE questions very easily. Let us take the first question. The maximum bending stress induced in a steel wire of modulus of velocity 200 kilonewtons per mm square and diameter 1 m when wound on a drum of diameter 1 meter is approximately equal to. That's what he has given. So we have to find out what is the bending stress induced in the steel wire. So a steel wire is taken. The modulus of velocity of the steel wire E is equal to 200 kilonewtons per mm square. E he has given, and diameter of the wire is 1 mm. This wire is wound on a drum. This wire is wound on a drum whose diameter is 1 meter. So the diameter of the drum is 1 meter, or otherwise the radius of the bent wire R is equal to 0.5. Because diameter is 1 meter, the radius is equal to 0.5 meters. That's all. That's the thing. So radius is equal to 0.5 meters. The diameter of the wire is 1 mm. So extreme fiber distance is half of 1 mm. So 0.5. So now you use the bending stress equation. M by I is equal to sigma by Y is equal to E by R. We want sigma. So sigma by Y is equal to E by R. So take sigma is equal to E by R into Y. E is Young's modulus given. R is 0.5 meters. So convert it to mm. And Y is 0.5 mm. So that will give you the maximum bending stress. So direct, slightly twisted question. That's all. You have to understand how to calculate R. R is nothing but half of the diameter of this drum. This drum is 1 meter diameter. So that part you have to understand. The basic assumptions of plane sections normal to the neutral axis before bending remain plane and normal to the neutral axis after bending leads to uniform strain over the beam cross section, uniform stress over the beam cross section, linearly varying strain over the cross section, stresses which are proportional to strains of the cross section. I have explained you this assumption. The basic normal, the basic assumption in the theory of simple bending is plane normal sections remain plane even after bending. Because of this, we say that the strain is directly proportional to the distance from the neutral axis, or otherwise the variation of the strain across the depth is linear. So linearly varying strain across the depth, that is the correct answer is C. The dimensions for the flexural rigidity of a beam element in mass m, length L and time t is given by. So what is flexural rigidity? Flexural rigidity of a beam is defined as the product of Young's modulus and its second moment of area or moment of inertia. Flexural rigidity is product of Young's modulus and moment of inertia, EI. So what is the units of the flexural rigidity? Young's modulus is newtons per mm square. Young's modulus is newtons per mm square. And I is moment of inertia is mm to the power of 4. It is second moment of area. I is equal to second moment of area. So area is mm square and second moment means mm into mm. So moment of inertia is mm to the power of 4. So newtons per mm square into mm to the power of 4. So this becomes, we get Newton meter square or kilonewton meter square. That is the units of flexural rigidity. Units of flexural rigidity are kilonewton meter square. So kilonewtons is force. Kilonewtons is nothing but the load or the force. Force is equal to mass times acceleration. Force is equal to mass times acceleration. So mass times acceleration. Acceleration is what? Acceleration is L by T square. L by T to the power of, so L by T square. That is why we get force is equal to mass into acceleration. So m into L into T to the power of minus 2. T square, L by T square. So if we bring up T to the power of minus 2. So this is for force. This is for the kilonewtons. mL T to the power of minus 2. This is for the force, mass into acceleration. Into meter square. Meter square is L square. So L square. So if you substitute this m into L square L cube T to the power of minus 2. This is the mL cube T to the power of minus 2 is the dimension for flexural rigidity. Flexural rigidity. So answer B is the correct response. A simply supported beam of uniform rectangular cross section of width B and depth h is subjected to linear temperature gradient 0 degrees at the top and t degrees at the bottom as shown in the figure. The coefficient of linear expansion of the beam material is alpha. The resulting vertical deflection at the midspan of the beam is, so he wants us to find out vertical deflection at the midspan of the beam due to this temperature distribution. 0 degrees at the top and t degrees at the bottom. Now this is a simply supported beam. This is a simply supported beam. So let us try to understand this problem. This is slightly complicated question. This is. It will take for you to solve this question 2-3 minutes to solve this problem. So this is a simply supported beam. This is a simply supported beam, and the temperature is varying from 0 degrees to T degrees centigrade. So at the neutral axis, if you take, the average temperature is T by 2, top 0, bottom is T. So at the center it is 0 plus T by 2, so it will be T by 2. Average change in temperature is T by 2 at the neutral axis. So because of this, what is the compression in the top fiber? We know because of temperature L alpha delta T. L alpha delta T. So accordingly, compression in the top fiber. So here you see, top fibers are getting compressed, bottom fibers are elongated because temperature is more at the bottom fiber. Temperature is more at the bottom fiber. Bottom fibers elongate and top fibers compress. Okay, top fibers compress. So the top fibers are in compression, which is equal to L alpha T by 2. Similarly, elongation in the bottom fiber will be L alpha T by 2. So it is L alpha delta T. So from this we get, what is the temperature strain now? L alpha T by 2. L alpha T by 2 is the change in length divided by original length. Okay, L alpha T by 2 by L. So we get the strain is alpha T by 2 is the temperature strain we are getting. So alpha T by 2 is the temperature strain. What is what we want? We want the deflection at the midpoint, which is downward deflection. You can see here. The midpoint is deflecting downward. What is the bending equation? M by I is equal to sigma y is equal to E by R. Sigma by y is equal to E by R. So the radius, the curvature is 1 by R is equal to sigma by EY, which is equal to, which implies 1 by R is equal to sigma by EY. So 1 by R is equal to sigma by E is nothing but strain by Y. Okay, strain by Y. Okay, strain by Y. So what is strain? It is H by 2. This depth is H. Y is H by 2. Extreme fiber distance is H by 2. So if you substitute that, we get 1 by R is equal to alpha T by H. Alpha T by H. It's very simple. Curvature is equal to sigma by EY. But sigma by E is nothing but strain. So E by Y. But Y is what? H by 2. H by 2. So if you substitute, you get 2 E naught by H is equal to alpha T by H. 2 E naught by H, that is equal to, E naught is equal to alpha T by 2. So you get alpha T by H. That is the 1 by R. But now, you know, this is from your intermediate knowledge, you know, this is the property of the circle. If you take a circle and if this is the chord length,
if you take the chord length, okay, the chord length, the equation is L by 2 into L by 2 is equal to delta into 2R minus delta. So this is delta, the downward deflection, and this is total diameter is 2R. So if you take delta remaining, so this portion is 2R minus delta. So from properties of the chord, L by 2 into L by 2 is equal to delta into 2R minus delta. Okay, delta into 2R minus delta. So L square by 4 is equal to 2 delta R minus delta square. So from which you solve for delta, which is the downward deflection, you get the answer. A slightly complicated question. So it is a temperature is varying from 0 to 0 at the top to bottom, T degrees at the bottom. Generally, if you take a practical case, it is reverse. It is a practical case if it is reverse generally, because if you take a slab, at the top of the slab the temperature will be more, at the bottom of the slab the temperature will be less. So in the room temperature, in the bottom of the slab generally will be at the room temperature, and if you are operating air conditioning, the bottom of the slab temperature will be very less, whereas the top of the slab, which is subjected to hot sun, will have higher temperature. So actually there will be hogging, it is not sagging, there will be hogging taking place because of the temperature distribution in a normal practical case. But this is the question asked like this, so we have to solve this problem in this way. You have to use the property of the chord property of the circle also this to find out this delta, that is the midpoint deflection. Because this is bent into we assume that this bends into a circular arc. This bends into a circular arc. So we have to use this circle principle also to solve this problem. A homogeneous, simply supported prismatic beam of width B, depth D, and span L is subjected to a concentrated load of magnitude P. The load can be placed anywhere along the span of the beam. The maximum flexural stress developed in the beam is. So it is a homogeneous beam. So we always assume that it is a homogeneous, simply supported prismatic beam. So the cross section he has given is width is equal to B, depth is equal to D. Width is equal to B and depth is equal to D, the cross section. It's a rectangular cross section. He is saying that the load can be placed anywhere on the beam. The load can be placed anywhere along the span of the beam. It may be at x is equal to 0, or at the midpoint, x is equal to L by 2, or at the other support. So the load can be placed anywhere along the span of the beam. Now what is the maximum flexural stress developed in the beam? He is asking us to find out the maximum flexural stress. So first of all, we have to find out what is the position of the load P, which will give you the maximum flexural stress. You know, flexural stress depends upon bending moment. You know, the stress depends directly on the bending moment. So wherever the bending moment becomes maximum, the flexural stress will become maximum along the length. So first we have to find out at which point, if you place the load, the bending moment will become maximum. So for a concentrated load, if you place the load at the midpoint, we get the maximum bending moment. So we know that. So that's why keep the load P at the midpoint. So if you keep the load at the midpoint, the maximum bending moment at the midspan occurs. It is WL by 4 or PL by 4. That's the maximum bending moment, because each reaction is equal to P by 2, P by 2, P by 2 into L by 2, PL by 4 is the maximum bending moment. So to achieve the maximum bending moment, you have to keep the load at the midpoint. So the load is kept at the midpoint. If you keep the load at the midpoint, the maximum bending moment is equal to PL by 4. So we got M now. If you want stress, M by Z we want. So what is Z? Z is equal to I by Y max. What is I now? BD cube by 12. Okay, BD cube by 12 for rectangular section. Y max is equal to D by 2. So what is sigma? M by I into Y max. So substitute M value PL by 4, I value BD cube by 12 into Y is D by 2. So you get 3 PL by 2 BD square. BD square is the correct answer. Answer D is the correct response.
A beam with cross section given below is subjected to a positive bending moment. That is causing compression at the top. Sagging bending moment is considered as positive. So he is taking sagging bending moment as positive. What is the value of the moment? 16 kilonewton meters acting around the horizontal axis. 16 kilonewton meters acting around the horizontal axis. What is the tensile force acting on the hatched area of the cross section is? So he is asking us to find out the tensile force in this region, in this hatched area. So if you want to find out the tensile force here, what we want to find out? First we have to find out the stress here. We have to find out the stress here and multiply this with the area. So we will get the force. So if you see the cross section of the beam, it is 100 mm width and the depth is 75 plus 25 plus 50, that is 150. It is 150. 150 by 100. The beam is 150 by 100 and the hatched portion is 50 by 25. The hatched portion is 50 by 25. So the area of hatched portion is 50 into 25. If you can find out the stress in the hatched portion, multiply the stress with area 50 into 25, you will get what is the force in this particular hatched portion. So that is what we have to do. So for that, we know sigma max is equal to m by I into y max. M he has given already. So moment of inertia you can find out 100 into BD cubed by 12. 100 into 150 cubed by 12, you get the moment of inertia. So what is the extreme fiber distance? 150 by 2. So if you take neutral axis at the center, extreme fiber distance is 150 by 2. So y is equal to 75. So find out what is sigma max now. M by I into y max. M is 16 into 10 to the power of 6 because he has given kilonewton meters. I have Newton mm I have converted into 10 to the power of 6 divided by moment of inertia 28.125 into 16 to the power of 6. 10 to the power of 6 into y max is 75. So if you substitute this, sigma max is equal to 42.67. So 42.67 is the sigma max. So what is where does the sigma max occurs? The sigma max occurs at the top fibers. It occurring at the top fiber. So what we want is, what is the stress at the hatched portion? So use the principle of similarity. This is the stress distribution. This is the stress distribution. Here at the top, the sigma max is equal to 14.22. So what is the stress here at the point A? So using the principle of two similar triangles, you can find out the bending stress at A as we can write 42.67 divided by 75 is equal to 25 divided sigma by 25. So like that you get sigma value. Sigma is equal to 14.22. So here the stress is 14.22. Here the stress is 14.22. But see, in the neutral axis the stress will be 0. So that's why what we have to do, we have to take half of this as the average stress. So half of this as the average stress acting on the entire hatched portion. So you take 14.22 divided by 2 as the average stress. So total force of the hatched portion is equal to average stress in the hatched region multiplied by cross sectional area. Average stress is 14.22 by 2. Area is 50 by 25. You multiply this 8.9 kilonewtons. You get the force acting in this hatched portion. Slightly complicated question. The following statements are related to bending of beams. The slope of the bending moment diagram is equal to the shear force. The slope of shear force diagram is equal to the load intensity. The slope of the curvature is equal to the flexural rotation. The second derivative of the deflection is equal to the curvature. Which one of the above statement is a false statement? That's what he is asking. Now let us examine each one. Let us take the first statement. The slope of the bending moment diagram is equal to the shear force. Slope of the bending moment diagram means first derivative of the bending moment diagram. So dm by dx. So what is dm by dx? Which is nothing but the shear force. So first statement is correct. the slope of the bending moment diagram is equal to shear force is correct. Now let's take the second statement. The slope of the shear force diagram is equal to load intensity. The slope of the shear force diagram means first derivative of the shear force. So dF by dx. dF by dx is equal to intensity of the load W. So we know W is equal to dF by dx. So the slope of the shear force diagram is equal to load intensity. It is correct. The third statement is the slope of the curvature is equal to the flexural rotation. The slope of the curvature is equal to flexural rotation. What is slope of the curvature? The slope of the deflected curve is not equal to flexural rotation. It is a wrong statement. The slope of the deflected curve is equal to this. It is called slope. EI d square y by dx square is m, and the first derivative d theta by dx is equal to d square y by dx square is called the radius of curvature. So the statement 3 is wrong. The statement 3 is the wrong. The fourth statement, the second derivative of the deflection is equal to the curvature. Yes, correct. D square y by dx square is equal to 1 by r is also correct. This is the wrong. The slope of the curvature is equal to flexural rotation is the wrong statement. So 3 is the wrong statement. So option C is the correct answer. So simple concept. The plane sections remain plane assumption in bending theory implies strain profile is linear, stress profile is linear, both strain and stress profiles are linear, shear deformations are neglected. So please see. The plane sections remain plane assumption. I have explained to you. The plane sections remain plane assumption in bending theory implies strain profile is linear. That's what I have told. The strain is directly proportional to distance from the neutral axis. So strain profile is linear. So that is answer A is correct. Somebody can jump to C. Both strain and stress profiles are linear. Here, actually, when the strain profile is linear, the stress profile is also linear. But that is not because of this assumption. This assumption, the plane sections remain plane assumption is leading to strain profile is linear. So it is, you should not jump to the C. C answer C. So you should provide answer A is the correct answer. The first moment of area about the axis of bending for a beam cross section is moment of inertia, section modulus, shear factor, or polar moment of inertia. First moment of area. What is first moment of area? First moment of area is A into X. If you take the summation, first moment, it is sigma area into Xi. Or I will explain you in a better way. What is section modulus after all? What is section modulus? Section modulus is equal to I by Y. Section modulus is equal to I by Y. But what is I? I is equal to second moment of area. So I is equal to AY square. So AY square by Y. AY square by Y. Z is equal to I by Y. I is equal to AY square. So AY square by Y. So Z is equal to AY. AY, that is first moment of the area. Z is equal to first moment of the area. So first moment of area is nothing but Z. Z is nothing but section modulus. So the answer is D is the correct answer. Consider the singly reinforced beam shown in the figure. Actually, this problem is, you can understand a bit of RCC also. A singly reinforced beam is the beam in which the reinforcement is kept only at the bottom. The reinforcement is kept only at the bottom, that is in the tensile zone. No reinforcement is kept at the top. So such a beam is called as a singly reinforced beam in RCC. Okay, he has considered a singly reinforced beam and two concentrated loads are applied P and P in the middle portion. Okay, the beam is of 3L length. So at a distance of L from each support, he has applied the concentrated loads. He has taken a cross section XX, and at cross section XX, which of the following statement is true at the limit state? At the limit state, the variation of stress is linear and that of strain is non-linear. First option. The variation of stress is linear and that of strain is non-linear. First of all, in pure bending theory, strain is non-linear is wrong. So please, the statement A is wrong. Now go to second statement, B. the variation of strain is linear and that of stress is non-linear. So this is correct. This is correct. The assumption, the plane normal sections remain plane even after bending. So that assumption leads to the strain being a linear strain distribution. So the strain varies linearly. Whereas in limit state, the stress doesn't vary linearly. This is the stress block. If you have read RCC, limit state method design of RCC, in the stress block, we assume that the strain varies parabolically like this. So that is why the stress distribution is non-linear, whereas the strain distribution is linear. So answer B is the correct answer. A 450 mm long plain concrete prism is subjected to concentrated vertical loads as shown in the figure. Cross section of the prism is given as 150 mm by 150 mm. Considering linear stress distribution across the cross section of the modulus of rupture. Considering the linear stress distribution across the cross section, the modulus of rupture in megapascals is dash. First of all, what is modulus of rupture? Modulus of rupture for concrete or any other material is defined as the maximum stress which the material can bear. That is called as the modulus of rupture. That is maximum permissible stress is called as modulus of rupture. So we have to find out what is the maximum stress. That's what he is asking. So the beam is subjected to two loads 11.25, 11.25. So 11.25 means each reaction is also 11.25. So the reaction here is 11.25. The reaction here is also 11.25. So we want to find out the maximum bending moment. So here the maximum bending moment occurs at Q or R. It is same whether at Q or R the maximum bending moment occurs. So here the maximum bending moment is equal to reaction multiplied by 150 mm. So reaction is 11.25, 0.15 meters. So that gives you the maximum bending moment. So stress is equal to M by Z. M by Z. So Z is equal to I by D by 2. He has given the cross section. The cross section is 150 by 150. So Y max is equal to 150 by 2. So 75. So I by Y max. I is equal to BD cube by 12. So for a rectangular section, we know Z is equal to 1/6 of BD square. So M by 1/6 of BD square. So if you apply that, you get modulus of rupture. A cantilever beam of length 2 meters with a square cross section of side length 0.1 meter is loaded vertically at the free end. The vertical displacement at the free end is 5 mm. So he has given us the deflection at the free end. So this deflection is delta B. The deflection at the B is 5 mm. The beam is made of steel with Young's modulus of 2 into 10 to the power of 11 newtons per mm square. The maximum bending stress at the fixed end of the cantilever is. So he is asking us what is the maximum bending stress at A. Maximum bending stress at A. So this problem can be solved. This problem can be solved by using the principle of deflection. So if a cantilever is subjected to a vertical load at the free end W, the deflection at the free end is WL cubed by 3EI. This we studied in deflections chapter. Okay, this we have studied in deflection chapter. So WL cubed by 3EI is 5 mm. So equate WL cubed by 3EI to 5. So only unknown in this problem is W. So WL cubed by 3EI is equal to 5 mm. E is known, I is known. Because I is known because B and D are given. One BD cubed by 12 will give you I. So WL cubed by 3EI is equal to 5 mm, from which you get W value as 3125 newtons. So once you get W value, we want to find out the stress here. So what is the bending moment at A? Bending moment at A is equal to W into 2. So 3125 into 2 is the bending moment. So 6250 Newton meters. So what is stress now? M by Z. For rectangular section, Z is equal to 1/6 of BD square. So calculate Z is equal to 1/6 of BD square and put M by Z. You get the maximum stress. Sigma max is equal to 37.5 newtons per mm square.
So this concept you have to use here. Delta B, the deflection at the free end is equal to WL cubed by 3A. He has not given us the W value. Without giving W value, he has given us the deflection value. So delta B is equal to WL cubed by 3A. You find out what is W from this, and then you find out bending moment at A as WL, and stress is equal to M by Z. That's all. Some of the questions which have appeared in the mechanical gate examinations, previous gate examinations, also we'll try to look at. So the first question is, two beams, one having square cross section and another circular cross section, are subjected to the same amount of bending moment. Okay, one beam is a square cross section, other beam is circular cross section. They are subjected to same amount of bending moment. If the cross sectional area as well as the material of the both the beams are same, then he is asking cross sectional area of the both sections is same. Material is also same. Material is same means Young's modulus is same. Okay. Cross sectional area also is same. Maximum bending stress developed in both the beams is same. Circular beam experiences more bending stress than the square one. The square beam experiences more bending stress than the circular one. See, as the material is same, both the beams will experience the same deformation. So the four responses are given. So first let us try to understand the problem. Let us say for the square section, the side of the square is A. For circular section, let us say D is the diameter. D is the diameter. So if you consider the square section, sigma is equal to M by Z or M by I into Y. Okay, so M by I is A to the power of 4 by 12, BD cube by 12, but B is equal to D is equal to A, so A to the power of 4, A to the power of 4 by 12 into Y is equal to D by 2, D is equal to also A, so A by 2, M by 4 into M by 4 divided by A to the power of 4 by 12 into A by 2, M by I into Y. So we get M into 6 by A cube, that is the maximum bending stress in square section. M into 6 by A cube. Similarly, let us try what is the maximum bending stress in circular section. So again M by I into Y. M by pi d square by 64. Moment of inertia is pi d square by 64. So M by pi d square by 64 into D by 2. So this gives us M into 32 by pi d cube. That is the maximum stress for a circular section. Okay. But he has given that both the sections are having same area of cross section. So now equate the area of cross section. So what is cross sectional area of this? A into A. So A square is equal to cross section of circular is pi d square by 4. So A square is equal to pi d square by 4, from which we get A is equal to 0.886 diameter D. A is equal to 0.886 D. So now you take the ratio of stresses. Sigma 1, sigma rectangle by sigma circle. Okay, sigma rectangle by sigma square by sigma circle. So 6m by A cubed divided by 32m by pi d cube. So you get the answer as 1.1286 whole cube into 0.84. So or otherwise sigma 1 by sigma 2 is equal to 0.847. Or otherwise sigma 1 is equal to 0.847 into sigma 2. So sigma 1 is less than sigma 2. So square section is, let's say, the square section is having lesser stress when compared to circular section. So answer B is the correct answer. The circular beam experiences more bending stress than the square one. So stress in bend circle is more than the rectangle. So always remember that circular section is uneconomical. Circular section is uneconomical. Even rectangular is uneconomical. It's better to go towards T sections or I sections or hollow rectangles or hollow circles, which are more economical sections. A cantilever beam has the square cross section of 10 by 10 mm. It carries a transverse load of 10 newtons. Considering only the bottom fibers of the beam, the correct representation of the longitudinal variation of the bending stress is. Very simple question.
you want longitudinal variation of the bending stress, that is variation along the length of the beam. So he has taken a cantilever with a center load 10 kilonewtons. So we find out bending moment. So if you want to find stress, stress is directly proportional to bending moment. So first we have to find out bending moment. Bending moment at free end is equal to 0. Okay. Bending moment at this point is also bending moment up to this. Bending moment up to this is 0 because there is no load on the right section. So bending moment at below the load. So I'll show the diagram. So let us say ABC is the cantilever. AB is the cantilever. C is where the load is acting at midpoint. The cross section is 10 by 10. Okay, bending stress is M by Z. So Z is equal to 1/6 of BD square. So that is 166.67 we can calculate. So between B and C there is no bending moment. You can take any section between B and C, there is no bending moment as there is no load on the right hand side. So up to C the bending moment is 0. So when bending moment is 0, bending stress sigma is also 0. So there is no stress between B and C, 0. Bending stress is 0. Bending stress at A is equal to bending moment at A divided by Z. Bending moment at A is what? 10 into 1. Okay, bending moment at A is 10 into 1. So 10 by Z, 166.7. So that is 60 newtons per mm square is the bending stress at A. So from here to here is horizontal line. From here it is 0. Here it is 60. So the variation is linear. Bending stress variation is linear. So straight line. So which response is correct? So you can see this response up from here to here is 0. At A it is 60. Variation is linear. So this response is correct. Answer A is correct. A simply supported beam of span 6 meters is loaded like this. Okay, loaded with a load of intensity 3 kilonewtons per meter. Loaded with a load of 3 kilonewtons per meter. So what is the maximum value of bending moment? It's having a 75 mm diameter, circular cross section. Okay, what is maximum bending moment? We know maximum bending moment for a simply supported beam is WL square by 8. So W is 3 into span is 6. WL square by 8 is the bending moment. Then what is the next question? What is the maximum value of the bending stress? Once you know the bending moment, bending stress is equal to M by Z. So Z is equal to pi d cube by 32 for circular section. Diameter is 75. So pi d cube by 32 will give you Z. Stress already you have calculated. Moment you have already calculated. So M by Z will give you the maximum bending stress. Two questions are linked to this question. A massless beam ABC, a massless beam, has loading pattern as shown in the figure. The beam is of rectangular cross section with a width of 30 mm and height of 100 mm. So the beam is 30 by 100. The beam is 30 by 100. Rectangular cross section 30 by 100. Along the span, it is loaded. It is a 4 meters length. So the right half portion is loaded with a UDL with 3000 newtons per meter intensity. 3000 Newton per meter intensity. So what does he want? What is the maximum bending moment? Where does the maximum bending moment occurs? So where is the maximum bending moment occurs? That's what the question. First question. So first we have to find out where does the maximum bending moment occur. So let us consider a section at a distance of x from right hand support C. Okay. Before that, we have to find out the reactions. In a simply supported beam, we have to first find out the reactions. So let us take reaction at A as VA, reaction at C is VC. Okay, take moments about any one support. Take moments about any one support. So if you take moments about A, VC into 4 is equal to 3 into 2 into 2 plus 1. Because the centroid acts at 1 meter midpoint, 1 meter. This is 2 plus 1.
So 2 plus 1, 3. So from this we get what is the reaction at C. VA plus BC is equal to total downward load. So 3000 into 4, 12,000 newtons. So 12,000 newtons. So that is the total load. So from this we get VA is equal to VC. VA is equal to 1.5. VC is equal to 4.5. So this is how we have to get the not 12,000. Sorry, total downward load is only 3,000 into 2 meters. 6,000 Newton per meter or 6 kilonewton per meter. So that is why VA is 1.5, VC is equal to 4.5. Once you know this, now we want to find out where the maximum bending moment occurs. So let us consider a section at a distance of x from the support C. So here mx, you try to write the bending moment equation mx. mx is equal to VC into x, vertical reaction at C into x, that is 4.5 into x, okay. VC is equal to 4.5 into x minus this intensity of the load is 3 into x square by 2. So this is the bending moment, okay. dmx by dx is equal to 0 you can make, or otherwise more easy is find out the shear force and equate it to 0. That also you can do. So try to write the shear force equation of this section. So shear force is here vertical reaction is 4.5 kilonewtons. Algebraic sum of all the forces on the right hand side I am considering. So vertical reaction is 4.5 and downward load is 3 into x. 3 into x. So the shear force equation is, if you follow right upwards positive, if you follow right upwards positive, so 4.5 minus 3x. 4.5 minus 3x, right? Sorry. Yeah, right upwards is positive. We are following 4.5 minus 3x. Equate 4.5 minus 3x is equal to 0. For the bending moment to become maximum, shear force should be equal to 0. So 4.5 minus 3x is equal to 0. So from which we get x is equal to 4.5 by 3 or 1.5 meter from C. So for the given problem, the maximum bending moment occurs at a distance of 1.5 meters from C. So that is the answer. So see here 2.5 meter, that is 2500 mm from right of A. Okay, right of A. So this way you can have 1.5 from C. So automatically 2.5 from A because it's 4 meters. Total span is 4 meters. So like this you can find out. Now the next question will be, what is the stress? The maximum magnitude of bending stress is. That's what he is asking. So stress, already we found out where the bending stress is becoming maximum. Okay, bending moment is becoming maximum. So find out where, what is the bending moment there. So find out here what is the bending moment. Bending moment is maximum at 1.5 from C. So here the bending moment is equal to vertical reaction at C. So 4.5 into 1.5 minus 3 into 1.5 into 1.5 by 2. That is the bending moment, maximum bending moment at the section. So if you take that bending moment, section modulus is BD square by 6. Already B and D has given. So BD square by 6 will give you section modulus. Sigma Z is equal to M by Z. So M is equal to 4.5 into 1.5 minus 3 into 1.5 into 1.5 by 2 gives the bending moment. M by Z gives you the stress. So like this you can calculate what are the maximum bending stresses that are occurring. So always remember to follow the basic concept. M by I is equal to F by Y or sigma by Y is equal to E by R. So all the problems we have solved, you can see, are depending upon the basic concept. We have not done, we have not remembered many things, or we have not done any complicated mathematics or anything in this. So if you try to follow the basic concepts, we are able to solve the problems given in the GATE examination. So that's why I always request or advise the students to understand the basic concept. So here the basic concept is, when the beam is subjected to loads, when the beam is subjected to loads or couples, a simple bending takes place and the beam bends into an arc of a circle.
an arc of a circle. If the load or the moment applied is m, the moment of inertia of the beam is I, and if the circle, it bends into a circular arc, if the radius of circle is r, if the radius of the circular is r, if the material Young's modulus is E, if sigma is the stress that is developed, and if y is the fiber distance where you are calculating the stress, then the simple bending theory states that m by I is equal to sigma by y is equal to E by r. E by r. So in this, we have assumed that plane sections, plane normal sections before bending remain plane and normal even after bending, which means the strain is proportional to y, that is the distance from the neutral axis. Neutral axis is the axis where the strain is equal to 0. In case of sagging bending moment, above the neutral axis we get compression and below the neutral axis we get tensile stresses. In hogging bending moment, with above the neutral axis we get tensile stress and below the neutral axis we get a compressive stress. Neutral axis, the stress is equal to 0, the strain is also equal to 0. Neutral axis doesn't undergo either elongation nor shortening, so strain is equal to 0. Because strain is equal to 0, stress is strain into Young's modulus, that is also equal to 0. So that is the neutral axis. So with these concepts, with these simple concepts, we can try to solve any problems. So section modulus we are defined. Section modulus is nothing but I by y, that is moment of inertia divided by extreme fiber distance. So I by y max. So we have found out section modulus for a rectangular section. So I is bd cubed by 12 and divided by b by 2. So we have got 1/6 bd square. Similarly, for a circle section modulus, we have found out as b once bd bd to the power of 4 by bd cubed by 64 is I, that divided by d by 2. That is the section modulus. So similarly, for hollow rectangular section, hollow circular section, we have found out the section modulus. It's very even that formula also you need not remember. Z is equal to I by y. You put that, you keep that concept. Z is equal to I by y. So if you keep that concept, the bending moment is equal to sigma into Z, or sigma is equal to m by Z. So please remember, m is proportional to Z. The carrying capacity of the bending moment for a given beam, for a given material is proportional to Z. So if m is proportional to Z, you can find out what is the a beam of uniform strength. So you design a beam of uniform strength. It is possible by varying either width or depth. We can keep the width constant and vary the depth, or we can keep the depth constant and vary the width. Accordingly, we can design a beam of uniform strength. So in my material which I promised to give you by the end of this course, I am going to give few more problems which will involve you the problems containing flitched beams and as well as the problems having uniform strength, beams of having uniform strength, that also I am going to give to you along with solutions, along with the explanation of the solution I am going to provide. So all the students can go through those material and by just keeping the concept in mind, try to answer these questions. Try to answer these questions. So don't mug up anything. Don't try to remember anything as far as possible. Try to simplify minimum things to remember. Try to minimize as minimum things as possible to remember. Don't give pressure to your mind. Okay, don't give pressure to your mind. Try to minimize the things you have to remember when you go to GATE examination. So by seeing the concept, by understanding the concept, tackle the problem. And as already I'm repeatedly telling you, the questions in the GATE examinations will try to test your understanding of the concept, not your memory capacity. So if you try to follow these concepts, you will be able to easily analyze any problem given in the GATE examination and successfully crack the GATE examination. So friends, this is about the simple theory of bending which we have discussed today and the various concepts related to this theory of bending, which is very much useful in structural design, Whenever you, as a civil engineer, you are doing a structural design, these concepts are very much useful, because you should know where the tensile stresses are developed, where compressive stresses are developed, so where the steel reinforcement is to be provided, where you need not provide any steel reinforcement. All this is governed by this simple theory of bending. So please try to understand the concept and try to find out the stress at any point in a beam, and then able to design the structure accordingly. So that's all for the day today. I wish you all a nice time in the evening. Spend your time trying to review whatever concepts we have given in the last 3 days and today. So come tomorrow morning with a fresh mind and with a revision of what we have discussed in today and on also last 3 days. So as we go along, I will take you along. I will take you along with me in trying to solve these gate questions by using purely concepts without much remembering any formulae. So that's what my approach is, and that's what I want you to follow. And uh, let us meet tomorrow afternoon at the same time, 3 o'clock. Till then, have a nice time. Bye bye. See you. Take care of yourself and take care of your family. Have a nice time. Goodbye. See you tomorrow.